Welcome to my talk. It's my great honor to present my work for the past 4 years with the title of Modeling Secondary Circulations in the Convective Boundary Layer using the Lijie simulations. Um, so our planet is covered with atmosphere. From the bottom to the top, we have different layers. For example, we have the troposphere, we have the stratosphere, we have the mesosphere, we have thermosphere, and the exosphere. But what we are interested most is the lowest part of the troposphere, because this is where we lived in, and this is where most of the weather phenomenon happens. So the Earth system models provide the current states of our planet. And to make those Earth system models more accurate, we have to understand the interactions between the land surface and the atmosphere. So allow me to introduce you a little bit about the atmosphere. So what is the convective boundary layer? So basically, boundary layer is the lowest part of the troposphere, which can reach its maximum to around 2 kilometers. So if you can see my screen here, so after this one, so after sunrise, because of the yes, maybe you can see now. So after sunrise, because of the constant income radiations, which is hitting the land surfaces, so the boundary layer was heated and increased and to the maximum. But after sun set, because there's no income radiation anymore, the land surface is gonna be lower than the atmosphere, then create the stable boundary layer. But in these studies, we only focus on the convective boundary layer. So you can say regard it as we're only focused on the daytime here. So how does the convective boundary layer looks like? We can start from the right side. So the convective boundary layer can also decompose into the three layers. From the bottom to the top, we have the surface layer, which is roughly 10% for the convective boundary layer. Then above it, it's a mixed layer, and above that is the entrainment zones. Theta, theta here is the potential temperatures, which has quite it's like a vertical lines for the potential temperatures in the mixed layer, but have like a strong inverse layers in the entrainment zones. On the right side is W prime theta prime is the turbulent heat fluxes. The turbulent heat fluxes decreased with the height and reaches the minimum at the entrainment zones, and the height which had the minimum value of the turbulent heat fluxes is used to determine the height for the boundary layer. Let's move back to the left side. So um, the physical process in the convective boundary layer can decompose into the non-local part and the local part. The non-local part are normally from thermals, and the local part are from the eddies. But people will uh, be curious, like where is the non-local thermals comes from? Let me remove the annotations first. So that is because our land surface is never it's never homogeneous. So in the actual world, we have a lot of heterogeneity of the land surfaces. For example, here we have the different land covers like the trees, the grass, the bare soils, and all those have the different properties. For example, the different soil moistures, the different roughness lengths, and because of those different properties, even you have the same income radiations to the land surface, they might have the different air temperature and the land surface temperatures. So on the right side, so simply when you have the warm area, the air goes up because it's warm and expand, and you have the lower density for the air. And when you have the colder area, then the air goes down. And because of this process, you can form a so-called inland breeze, so a circulations. And this circulation is called the secondary circulation, which happens at a scale of a couple of 100 meters or several kilometers. So we have a couple of research questions here. First, how do if we impose some background wind or ambient winds, will that affect the formations of the secondary circulations? And do we have indicators to describe the strength of the secondary circulations? The secondary question is like if we have the different heterogeneous scales, will that affect the formations of the secondary circulations too? The last question is like because we might have the flux imbalances, and if we're using these things, can we improve the representation of the fluxes and the Earth system models? And by that, we can improve the predictions. So I will briefly introduce you from the four parts. First, a simple description of the models that I was using for this work, the iconcyhedral non-hydrostatic models. Then we have this three different work packages. The first one is how soil moisture heterogeneities induced secondary circulations with ambient winds, which have been published on the Quarterly Journal of Royal Meteorological Society. The second work package is to assess the different flux imbalance prediction models. The third practice is if we can use these models, can we improve the representation of the heat fluxes in the Earth system models? First of all, this is the iconcyhedral models. So based on its name, so iconcyhedral is basically described our Earth in 20 phases, like it's iconcyhedral. So this model is a fully compressible atmosphere models covering all scales from the climate model to numerical weather prediction models and to larger simulations. The figures below just want to show that the simulations I used in my work is double periodic boundary conditions, which means everything goes to the right, but comes back to the left, and everything goes to top, will come back to the bottom to make it like infinite areas in my simulations. On the right side is the simple way how we couple the icon, the atmosphere models, with the land surface models called TerraML. And below is just some equations. I will not jump into the details, but here is just like the conservations of the mass, the conservation of the momentals, and the conservation of the energies in the models. So let's now move to my first work package about soil moisture heterogeneity-induced secondary circulations with ambient winds. In these simulations, the setup is a flat river corridor mimicked by the continued soil moisture distributions. So we have a river in the middle of the corridors, which is the saturated soil moistures here, then drying along to the edge. And because of this setup of the soil moisture, when you have the constant incoming radiations, then you will have the different land surface temperatures in the below, because we will have the different sensible heat fluxes and the different latent heat fluxes. Sensible heat flux is something used to change the temperature of the body, but latent heat flux is something you observe the energies, but you do not change the skin temperatures. It's just to change the phase of the water, for example, from the liquid to the vapor. And we add some ambient winds from the different locations and with the different amplitude. So we have the wind close to the river, we have the wind parallel to the river, or we have the wind directions in between, which is the mixed wind. And on the right side is the wind settings. The wind speed ranges from 0 meters per second to maximum 60 meters per second. Here, the model domain covers 4.8 times 4.8 square kilometers and consists 96 times 96 pixels for the size of 50 meters. And the simulation lasts 24 hours with the constant income radiations for 7 watt per square meter. This slide just to describe simple scaling parameters used here. We're using these scaling parameters is because we want to do some dimensional analysis, or let's say the similarity analysis. Then the conclusions is more common, and we can apply. For example, something I measured here, I can apply it in somewhere else. I will not jump into the details about those scaling parameters here, On the right side, it's how we decompose the atmosphere states into the ensemble average, into the mesoscales, and into the turbulence part. The result is very interesting here. So let me first introduce here. So because we have the flat river corridors, so you have the saturated soil moisture in the middle, and because it's much wetter, so it's actually cooler because you have higher latent heat fluxes because you use more energies to change the water phase from liquid to the vapor. And at the edge, you have less latent fluxes because you use more energies to increase the skin temperatures. So on the edge side, you have the red colors, which means the air goes to up. It's an updrift. And in the middle, as the air goes down, it's a downdrift. So the color represent here is like the red for the vertical wind is positive. The air goes up. And for the blue one is the downdrift. The air goes down. So because of this, we have formed the secondary circulations, and the structure is persisted when the parallel river wind, no matter how large of the wind speed, even the structure is persisted under 60 meters per second. However, when the wind comes from the cross river, then the structure was destroyed when the wind speed is large enough, for example, at 2 meters per second in my studies. A same result was observed when the wind from like mixed wind. And based on this, we do some like statistics. This one is the profile of the variances for the vertical wind, for the horizontal wind, and for the potential temperatures. And most interested in this figure is that we found that the peak value for this mesoscale vertical wind can represent the structures or the strengths of the secondary circulations I showed in the previous slide. And we made some like dimensional analysis with these peak values as an indicator for the secondary circulations with some commonly used parameters. Here we have the Bohr ratio. So Bohr ratio is the ratio of the sensible heat fluxes to the latent heat fluxes. So describing the distribution of the energies to increase the temperature or to change the phase of the water. Then we have minus Zi over L. So Zi is the boundary layer height, L is the Buch's length. So you can just say the larger of the values, the more convective of the boundary layer. And we also have the heterogeneity scales. So the larger of the heterogeneity scales, of course, you have the larger of the heterogeneities here. We found that positive correlations between the secondary circulation strengths with those commonly used scaling parameters here. This slide shows that when the secondary circulation structure is there, then the turbulent heat fluxes is decreased, while the dispersive or the horizontal advection fluxes is much larger, which means this turbulent heat flux is something that we want to measure, and you can regard the other two more or less like the arrows. And because the decrease of the turbulent heat fluxes, then you have a higher flux imbalances. Okay, now let's move to the second work packages. So we extend the land surface from more like one-dimensional heterogeneities from the river corridor to two-dimensionals, the checkerboard pattern here, but we make it very simple. So here we have basically the dry area and the wet area, but we make the different heterogeneity scales, ranges from, for example, 2.4 kilometers, which termed as S4200, and we have 1.2 kilometers, we have 600 meters, 300 meters, 150 meters, and 50 meters. To be clear here is the domain area is the same, but the grid size is also the same. I mentioned here on the right side, but the heterogeneity scale is different. And we want to study how these scales affect the structure of the secondary circulations. The simulation lasts for 8 hours, and we also use the last hours for the analysis here. And the result is more interesting here is because when the heterogeneity scale is large enough, we found that the first column, the first row is for the vertical wind. The second row is for the turbulent heat fluxes, and the last row is for the sensible heat flux and the surface. We found that when the heterogeneous scale is large enough, then we have a good correlations between the vertical wind, or let's say the updrift, with the sensible heat fluxes. And this structure patterns, you can still observe them until when your heterogeneous scale decreased to 300 meters. And we also made a homogeneous simulations here for reference, and we found that when the heterogeneous scale is small enough, then the structure is kind of randomized, and we can say we found two different secondary circulations dominate the atmosphere, which is determined by the heterogeneous scales here. So we have the thermally induced mesoscale circulations, and we also have the turbulent organized structure circulations here. Now let's do some statistics again here. We decompose the heat fluxes into the turbulent heat fluxes, the dispersive part, and the advection part. And again, this turbulent heat flux is what we want. So we here define the flux imbalances is some part which is not captured by the turbulent heat fluxes to the ratio of the total heat fluxes. So the larger of these values, flux imbalance means the worst of the performance for the model. So we found here the flux imbalance is increased with the height. Okay, then we did the quadratic analysis. So we decomposed the heat fluxes into the four quadrant or the four classes. When both of the W prime or here is A prime positive and the W prime is positive, then it's termed the ejections. And when both of them are negative, then it's termed the sweeps. Oh, sorry. Then the other two have the outward interactions and inward interactions here. And you can calculate the flux contributions or the time fractions from different quadrant. On the right side is the box plotted of the flux contributions and then the time fractions from the ejections, the sweeps, and the difference of them. And what we found here is that the differences between the ejection and the sweeps also increased with the height, which can explain the increase of the flux imbalances. We did some, we select four flux imbalance prediction models because based on the literatures, these flux imbalance models can also be quantified based on some simple empirical equations here. So we select four of them and make comparisons with our data set. On the right side, we found the H08, which is the first one, have the worst performances, but the second one, the 18 and the Z19, have the quite similar performances that they have a good performances when at the lower part and a little bit on estimations with the increase of the height. The last model have the best performances here, but only when the heterogeneous scales is matched with our model setup here. So this result is very promising that we can using those models to represent the flux imbalances. So now let's jump into the third work package, which is inspired by the result of the second work packages. Since these flux imbalance models can quantify the part of the energy or part of the fluxes which is not determined or observed by the turbulent heat fluxes, why don't we use these flux imbalances to improve the prediction of the models? So I will not jump into the derivation of the equations here, but the result is like if we use the flux imbalances, we can correct the heat fluxes in the models here. So this is the workflows for the things we developed in the models. So basically, we just updated for the lowest atmosphere layers to improve the representation of the heat flux in the systems at each time step here. So to test this, we do both in large Eddy simulations and in the numerical weather prediction here. So in the large Eddy simulations, we're still using the icon and it's offline simulations. So here we prescribed the heat fluxes in the land surfaces. We have a little bit larger heat flux in the middle stripes and a little bit lower lower heat fluxes in the along side. Then it's expected that when you have a larger sensible flux in the middle, the air goes up, and the lower sensible flux goes down and form the secondary circulations here. Um, we also have numerical weather predictions. So larger simulations is atmosphere models works with the grid size around like 50 meters, 100 meters. But for the numerical weather predictions, it's often works with several kilometers here. Here we're using the ICO single column mode, but it's online simulations, which means it's coupled with the land surface models. The first data were obtained from the measurements conducted over the atmosphere radiation measurements program site in Oklahoma in 1997. This is the result for the flux imbalance here. So very clear patterns of the secondary circulations observed. So we have larger air temperature anomalies in the straps with the higher sensibility fluxes and the lower anomalies for the lower sensibility flux clear, right? And on the right side, on the middle column, then in the middle of the domain, the air goes up, and along the side, the air goes down and forms these circulations here, and also clears for the horizontal wind speed. So the wind goes to the both side, goes to the both side. Red means goes to the right, and blue means to the left, and forms these circulations here. And how the performance is, because we only run the one simulations here, so we select some subregions, like randomly select subregions for 50 samples at different scales. The subregion size ranges from 50 meters, 100 meters, 200 meters until 9.6 kilometers. And it's clear that if the green one is the original case theory, like without include the flux imbalance prediction models, and the other two is include these models, and the normalized flux imbalance is closer to one. So these figures tells people that by including the flux imbalance prediction models, we can improve the representation of the heat fluxes in the Lijie simulation. Similar result were also obtained in the numerical weather prediction here. So this is more dynamic, and especially in the convective bond layer, like simulation hours of 6 to 8, we have the very good performances that we decreased the flux imbalances. We also compared because we kind of like using the flux imbalance models to correct the heat fluxes. We want to make sure that the model is numerically convergent here. So at 6 hours, the heat fluxes have like a difference value of 0.07 Kelvin, then increased to 0.1, but decreased again because when we're using the flux imbalance prediction models, when you update the heat fluxes, you also update the boundary layer height, which is like a negative feedbacks to the system. So the model will not crash because you're using the flux imbalance prediction models, because we have negative feedbacks for the numerical divergence here. So this is the result. Secondary circulation structure persists on the parallel river wind and independent of the wind speed, but it's destroyed when the cross river wind is stronger than the mesoscale horizontal wind speed, which is 2 meters per second in our studies. The secondary circulation strength positively correlates with the Bowman ratio, with the stability parameters, with the heterogeneity parameters under the cross river wind. Then when you expand the heterogeneities to the two-dimensional, we found that with the decrease of the heterogeneity scales, two different schemes of the submesoscale circulations are observed, shifting from the thermally induced mesoscale circulations to the turbulent organized structure. Then improved asymmetric turbulent contributions from the sweeps and from the ejections improve the flux imbalance along the height. Last but not least, the flux imbalance prediction models has the potential to improve the model performance here. Thanks.